All right. Greetings, scholars. Beautiful mind here. And so we're going to go ahead and get started with chapter 4 on trigonometric functions. We're going to start off with section 4.1, angles and their measure. A few objectives here. 1, learn the vocabulary associated with angles. 2, use degree and radian measure. 3, convert between degree and radian measure. 4, find complements and supplements. 5, find the length of an arc of a circle. So angles. A ray is a portion of a line made up of a point called the endpoint and all points on the line on one side of the endpoint. An angle is formed by rotating a ray about its endpoint. The ray in its original position is called the initial side, while the ray in its new position after the rotation is called the terminal side. The endpoint is called the vertex of the angle. Okay. For whatever reason, when I see ray, I think of like Kamehameha Blast in Dragon Ball Z, right? That's a ray. This is just the image I always get when I think of ray. So that's how I always visualize it. If the rotation of the initial side to the terminal side is counterclockwise, the result is a positive angle. So counterclockwise is positive. If the rotation is clockwise, the result is a negative angle. Angles that have the same initial and terminal sides are called coterminal angles. So the initial side is where we start. The terminal side is where we finish. If it rotates counterclockwise, it's positive. If it rotates clockwise, it's negative. And then angles that have the same initial and terminal side are called coterminal angles. An angle in a rectangular coordinate system is said to be in standard position if the vertex is at the origin and its initial side coincides with the positive x-axis. Okay, so we call that in standard position. Counterclockwise is positive, clockwise is negative. If the terminal side of an angle in standard position lies on the x-axis or the y-axis, the angle is said to be a quadrantal angle. Pretty straightforward. If the terminal side of an angle theta lies in a quadrant rather than on the coordinate axis, we say that theta lies in that quadrant. So again, the quadrants are counted. Top right is 1. So here, let me just label that real quick. So top right, this is quadrant 1. This is quadrant 2. This is quadrant 3. And this is quadrant 4. So here we're asked to draw each angle in the standard position, okay? So then for A, we want a 60-degree angle. That should put us where? In quadrant 1. So if that's 45, 60 is like right about here. And we went this direction. Positive is counterclockwise, right? 135, so directly vertical is 90, horizontal is 180, so 145 is halfway between those. It's going to put us about here. And that one, this was what, 60 degrees? This one was 135 degrees. Negative 240 is what, clockwise? So let me see, 90, 180. I think the next one is what, 270? So is that like 60 degrees off the x-axis and quadrant 2? So something like this. So if that's 45 about here. So then our theta, we went in this direction. And then 405, so we do a full 360, and what's left over? 45 degrees. So that should put us in quadrant 1. And our theta, we started here, we did a full rotation, and then we finished here. Again, that's our theta. Okay. And so these are the results we got. Let's compare this to our prepared notes. 60-degree angle in quadrant 1. 135-degree angle in quadrant 2. Negative 240 in quadrant 2 going clockwise. And then 405. It basically puts us at a 45-degree angle in quadrant 1. Okay. So now we're going to explore the relationship between degrees, minutes, and seconds. Now, honestly, for this one, I just commit these two to memory. 60 seconds makes up 1 minute, and then 60 minutes makes up 1 degree. And then from there, I just use that for my conversions. Let me undo that. All right, I just commit these two to memory. Once you have these two, you can get all the other conversions. So that's the way I go about that. So radian measure. An angle whose vertex is at the center of a circle is called a central angle. A positive central angle that intercepts an arc of the circle of length equal to the radius of the circle is said to have a measure of 1 radian. So we have a central angle that makes, an arc length of the circle. When that arc length is the same length as the radius of the circle, that's what we consider to be 1 radian. So in a full 360 degrees, we have a total of 6.28 radians. 6 full radians and then 28 hundredths additional a radian left over. Okay. So the radian measure theta of a central angle that intercepts an arc of length s on a circle is defined by this. Theta equals s over r radians. The way I remember this one, I tend to do s equals r theta. So the arc length equals our radius times our theta. That's what you see in purple is how I commit that to memory. Okay, and then when it comes to this one, so converting between degrees and radians, I just commit this to memory. 180 degrees equals pi radians. And then I just do my conversions. So once you see how we do conversions, if you get this one, you get everything else. I call these like twofers. For this, just knowing this one thing, you get 2 or more things automatically. Okay. So for instance here, we're asked to convert each angle in degrees to radians, okay? So we're given 30 degrees. I'm going to put this over 1. Now if we want to go to radians, now just a moment ago we said 180 degrees corresponds to pi radians. Okay. So when we go to do our conversion, because we have degrees on top, when we do our conversion, degrees need to be on bottom. So then 180 degrees corresponds to pi radians. Okay. The units of degrees are going to cancel. Okay. Now we can cancel those trailing zeros. 3 into 18 is 6. So it looks like it's going to be pi over 6 radians. Let me see. I think they kept radians. Okay. So for B, we have 90 degrees. And again, this over 1 is something that I introduce. That's how I do my when I'm doing conversions. I just introduce that. Okay. So then 90 degrees again, I'm going to go ahead and put it over 1. And that's a 90 degrees. So when we do our conversion, since we have the units of degrees on top, when we do our conversion, the units of degrees need to be on the bottom. So 180 degrees corresponds to pi radians. Okay. The units of degrees are going to cancel each other. We can cancel those trailing zeros. 18 divided by 9 is a 2. So we finish with pi over 2 radians. Okay. And then for C, we have this negative 225 degrees. I'm going to put it over 1. We said what? 180 degrees corresponds to pi radians. Okay. So because we have degrees on top, when we do our conversion, degrees need to be on bottom. Pi radians. Okay. Units of degrees are going to cancel each other. I'll just see if I can pull this up here. See if I can get this to work. There it is. I saw it. I saw it at the bottom right there. There it is, this one. Cool. Okay. Okay, so we got what? That 225, let's do 225 divided by 180 as a fraction. So negative 5 pi over 4. Radians. Okay. And then 55 degrees over 1. Again, because degrees are on top, when we do our conversion, degrees need to be on bottom. This cancels that. 55 over 180. I'll just put it as 11 over 36. Okay. Pi over 6, pi over 2, negative 5 pi over 4, 11 pi over 36, pi over 6, pi over 2, negative 5 pi over 4, 55, well, 0.96 radians. So you just have to crunch that number to generate that number. Okay, here we're asked to convert each angle in radians to degrees. Now we're going from radians to degrees, okay? So for part A, we have what? Pi radians over 3. Now we don't need the over 1 in this case because it's already a fraction. And then the conversion we said was what? 180 degrees corresponds to pi radians. So when we go to do our conversion, because radians are on top, that means radians need to be on bottom. So pi radians under 180 degrees. The units of radians are going to cancel, right? The units of pi are going to cancel. Something divided by itself is 1. And that looks like it's 60 degrees. Okay. Negative 3 pi over 4 radians. Negative 3 pi over 4. 3 pi radians over 4. Okay. So because radians are on top, when we do our conversion, radians need to be on the bottom. Pi radians under 180 degrees. The units of radians are going to cancel. Pi is going to cancel. So 45 times 3, 120. Plus 15, 120, 135. Looks like that was a negative 135 degrees. My chihuahua is snoring like a grown man. It is hilarious. Okay, we'll check this in just a moment. Let me see. 3/4 of 180. Should be 135. Okay, we're good. And then for C, 1 radian we want to convert to degrees. So 1 radian. Again, I'm going to put that one over 1. I'm going to say times. So we need radians on bottom, so pi radians. 180 degrees. The units of radians are going to cancel. And 180 over pi degrees. And then you just use your calculator to crunch that number. Okay, so let's compare this to our prepared notes to see how we did. 60, negative 135, 180 over pi degrees, 57.3 approximately. Okay. So complements and supplements. 2 positive angles are complements or complementary angles if the sum of their measure is 90 degrees. 2 positive angles are supplements or supplementary angles if the sum of their measure is 180 degrees. Here we're asked to find the complement and the supplement of the given angle or explain why the angle has no complement or supplement. So complement adds up to 90, supplement adds up to 180. So then the complement of 73, we would do what, 90 minus 73? What is that, 17 degrees? So the supplement, we wanted to add up to 180. So we'd say like 180 degrees minus 73 degrees. If that were 80, that'd be what, 107? Okay. So for B, we can't find a positive number to add up to the given degree to get to 90. So we would say none for that first part. And then the supplementary angle. So we would say what, 180 minus the 110. What is that, 70? Okay, so we got 17, 107, none, and then 70. 17, 107, none, and then 70. So arc length formula, S equals R theta, where r is the radius of the circle and theta is in radians. So s is the length of the arc, right? So arc length, s equals r theta. We kind of mentioned this, but that's how I remember it. The main takeaway here is that theta needs to be in radians. So whenever we're using that theta, we got to make sure that it's in radians. A circle has a radius of 18 inches. Find the length of the arc intercepted by the central angle with a measure of 210 degrees. Okay. So we just said what? S equals r theta. Theta in degrees, in radians. Okay. So we're trying to find the arc length. The radius is 18 inches. Now, we got 210 degrees. We need to convert that from degrees to radians. Over 1. Now, before we said what? 180 degrees corresponds to pi radians. Okay. So when we do our conversion, in this case, because degrees are on top, that means degrees need to be on bottom. Pi radians. Okay. So units of degrees are going to cancel. The trailing zeros cancel, so like that cancels that. They're both divisible by what, 3? 7 pi over 6. So radians is essentially a unitless measure. It really doesn't have a unit. So here we would put 7 pi over 6. Like if we say a radians times inches, the final answer is going to be in inches. It gets like, the other unit absorbs radians. Okay. Let's see, what is that, a 3? 21 pi inches. About like 34, no, 60, 64. 65.97 inches. We'll say approximately 65.97. Okay. All right, let's compare this to our prepared notes. S equals r theta, 7 pi over 6, approximately 65.97 inches. So they showing off to the side, converting from degrees to radians, 7 pi over 6 radians. Okay. So in this example, we obtain the latitude of a location L anywhere on Earth by first finding the point of intersection P between the meridian root L and the equator. The latitude of L is the angle formed by the rays drawn from the center of the Earth to the points L and P, with the ray through P being the initial ray. Okay. So we have the central angle and arc length. And we got the latitude comes from that point P on the equator, and the central angle formed by, in this fashion. So Billings, Montana is due north of Grand Junction, Colorado. Find the distance between these two cities. Use 3960 miles as the radius of the Earth. Okay. So, not gonna lie, I did this before, and so what I did initially, I found the arc length of like the first latitude and then the second latitude, and then I subtracted my answers. So that entailed me having to calculate, like convert between degrees and degrees, minutes, and seconds. I had to do the conversions twice. So then I discovered a more sophisticated, I can barely say the word, more sophisticated way to go about it. So instead of finding the arc length of each one individually and subtracting it at the end, I'm going to subtract in the beginning, right? It makes it so much more simple, right? So let's see if we can do this. So we got the 4548 minus the 3907. Okay. So let's do like this. We got now 45 degrees, 48 minutes. We want to subtract 39 degrees and 7 minutes. Okay. Now I think we got a little bit lucky with the way the numbers kind of fell. So I think we can do the 48 minus 7. We should be able to get 41 minutes there. And then, what is that? 6 degrees there. So 6 degrees and 41 minutes should be the distance from one city to the next as far as degrees. So now we got to convert from the we're going to convert from degrees to radians. So first we need to convert the minutes to degrees. Okay. So I'll kind of work here. So we have 41 minutes. I'm going to put that over 1. Now, how many minutes in a degree? I think it's 60 minutes corresponds to 1 degree. So then units of minutes are going to cancel. So then whatever 41 over 60 is. Let me see. So what if I do plus 6 and then I hit math as a fraction? Okay. So as a decimal, the 41 minutes is going to be 0.683 bar degrees. So then our total degrees are going to be 6.683 bar degrees. As a fraction, I'm going to use the fraction just because it's exact. So that's going to be, those units are going to be degrees, right? So that means we're working with 401 over 60. Let me change how I write that. 60, these are degrees. It's like 6.683 bar degrees is what that number is. So now this is our theta. Right? So we can use S equals R. Oh, wait, nope. Before we can use S equals R theta, we need to convert from degrees to radians. All right? So as before, we said 180 degrees corresponds to pi radians. Okay? So then if we have 401 over 60 degrees, we're going to say times, since degrees are on top, then when we do our conversion, degrees need to be on bottom. 180 degrees corresponds to pi radians. Okay. Units of degrees are going to cancel. And then we just need to crunch that number. So we'll take the 401 over 60. We're going to say times pi over 180. And this will be the units of radians. Can I hit math as a fraction? We can't do the fraction anymore. Now, really, we should be writing this long decimal because you really don't want to round until you get to the end. If we round too early, it'll throw things off. So I'll say it's approximate. I'm going to write the long decimal. 11, 66, 46, 17, 17. Okay? Radians. I'm going to go ahead and include my units, radians. Okay? So now, almost there. And again, now I think we're ready to use S equals R theta. So then the arc length is our R, which is the 3960 miles. Times, I'm just going to reference this as star. So times star. Okay. So we want to take that answer and multiply it by 3960. And and 461.92 miles. Okay, let's see how did we do. Come on. I just can't. There it is. Okay. All right, so we got 461.92 miles. Okay, let's see how do we do. So because Billings is due north of Grand Junction, the same meridian passes through both cities. The distance between the cities is the length of the arc S on the meridian subtended by the central angle theta. That is the difference between their latitudes. So then 6.4 or 6 degrees and 41 minutes. All right. Let me see. 463. Okay. So I'm sure it's like rounding. So like if you're on like a testing environment, or mainly the tests. The other ones you get unlimited attempts. Just do the best you can. You can challenge these though, like because it's like they rounded at a different point in a different way that we did. For instance, they used approximately 0.117 radians, where we used the long decimal, so that's why it's different. But you can see 0.1166 rounds to 0.117, right? And the homework is usually pretty specific about like rounding and stuff of that nature. But generally speaking, we want to try to keep it as exact as possible and only round at the end. Whenever we get a long decimal along the way, really we're supposed to write out the long decimal and only round at the very end, okay? But yeah, then when you start rounding earlier, then it kind of skews it. So you want to give yourself plenty of space, write big, neat, legible, and organized, and that helps. Like how I was writing in a small space in that last example was counterproductive, right? Okay. But nonetheless, we're pretty much there, and we got both of them. Okay. And so with that, we're going to go ahead and end the session here. And from one beautiful mind to another, have a wonderful day. Take care and peace.